Chapter 28, Problem 51. A log is sitting on an inclined plane. This log is wrapped with a bunch of wire that's carrying a current. At the same time, there's a uniform magnetic field pointing straight up, as shown. The question is, how much current do you need to send through that coil of wire to keep that log stationary? Step 1. The log remains motionless, so this is a job for statics, which really means it's a job for the force analysis method, setting acceleration equal to 0 because nothing's moving, or speeding up or slowing down. Step 2, I'm going to use an x-force inventory. Step 3, there are the sums of all of my x-oriented forces. Notice that I rotated my coordinate system to minimize the amount of decomposition. The one vector I do have to decompose is the weight vector. Step 4, again, because this log is remaining motionless, the acceleration is equal to 0. Step 5, I have an expression for static friction. Step 6, I'll continue with the y-force inventory. Step 7, I'm summing up all of the y-oriented forces. Once again, remembering that nothing's moving here, so step 8, I'm setting the acceleration for the y direction equal to 0. Step 9, I now have an expression that links the normal force to the y component of the log's weight force. Step 10, I'm not able to see any evidence of the current in anything I've done thus far, so I'm going to go on to torque analysis in step 11. My knee-jerk reaction is to take all of the forces that I identified and see what torques they may contribute. Sum of all the torques equals rotational inertia times angular acceleration. That's Newton's second law for rotation. In step 12, once again, this is an equilibrium, which means no acceleration, and that's true for linear as well as rotational acceleration. Step 13, I can see how the normal force as well as the x and y components of the log's weight force all originate at the center of mass of the object, which by the way is the same point I'm using for my axis of rotation. So remembering what torque arm is, I can see that there are no torque contributions from the normal force or the x or y weight component forces. Step 14, I'm saying the static friction force produces a clockwise or negative torque, and the magnetic force is contributing a counterclockwise or positive torque. Let's look at this in more detail. There's my static friction force. There's my torque arm, which by the way corresponds to the radius of the log. And here's an interesting note. You don't see any magnetic force vector present on this free body diagram. That's because, as was mentioned, for a current carrying loop exposed to a magnetic field, there is no net magnetic force, but there is in this case a torque. Step 15, I do have an expression for the torque produced by magnetic force on a current carrying wire, and specifically this is a constant current carrying wire exposed to a uniform magnetic field. Special note about step 15, I'm using what's called the pop can right hand rule, which means I shape my right hand as if I'm holding a can of pop with my thumb extended. And because the expression is ni vector A cross vector B, I orientate my right hand so that I'm able to swing vector A into vector B. If I do this correctly and maintain the proper shape, my fingers are going to be pointing in the counterclockwise direction and my thumb will be pointing out of the screen. Step 16, I'm just reiterating the fact that there's no net magnetic force on this constant current carrying loop in a uniform magnetic field, but there is a net torque produced by the magnetic force. Step 18, so my torque inventory yields the following. Step 19, once again, the torque arm for the static friction force is the radius of the log, because torque arms are defined as the position vector originating at the axis of rotation and terminating at the point where the force is applied. The angle between these two vectors, the static friction force and the position vector, also known as the torque arm, is 90 degrees. Step 20, looking again at the expression for the torque produced by the magnetic force, I need to be careful with that angle beta. Angle beta is the angle between my surface normal area vector and the magnetic field vector. Let's go back to our diagram. There's my surface normal vector. It's normal to the loop plane. The magnitude of this vector equals the magnitude of the loop area. How do I know it's pointing in that direction and not the opposite direction? It's because the convention is to take your right hand rule, the pop can right hand rule, wrap your fingers in the same direction as the current flow, and your thumb points in the direction of the surface normal area vector. My magnetic field vectors are shown as going straight up. So here I have the angle beta, which is the angle between the surface normal vector and the magnetic field vector, equals theta. Make some drawings on a piece of paper with a pencil and make sure that you satisfy yourself and agree that angle beta is the same as angle theta. Step 21, so I now have expressions for the torque produced by the magnetic force and the torque produced by the static friction vector, and now I can solve for I, the current that's traveling through the loops of wire wrapped around that log to keep it motion motionless. Step 22, I know that the area of a rectangle is length times width. The length L is given and the width equals twice the log's radius. Step 23, there's my updated expression for I. Everything is known I can solve. Step 24, there's a ton of good stuff in this problem. I had to deal with force analysis, torque acting on a constant current carrying loop in a uniform magnetic field, right-hand rules, challenging trig, and maybe even stuff I'm forgetting about.